Let's look at the problem 2300, successful pairs of spells and potions. So for this problem, we're going to provide a binary search solution. So first, we'll look at the statement of the problem. Then we analyze one example. Then we will prepare the code, and then finally test the code for several special cases and the generic case. So in generally, binary search is a very easy but powerful method. So the same line of ideas can be used to solve a variety of problems with different levels of difficulty. So here, maybe we regard it as an example and a start. First, let's look at the statement of the problem. So we are given two positive integer arrays, spells and potions, of length n and m respectively. So where the element in spells represents the strength of the S spell, and similarly, the element in the portions represents the strength of the J portion. So we are also given an integer success, so which actually specifies a bound for a successful match. So it speaks like a spell and a portion pair is considered successful if the product of their strengths is at least success. So in this problem, we are required to return an integer array called pairs of length n, where each of the elements is the number of portions that will form a successful pair with the ice spell. So that's the statement of the problem. So here is the constraint of the problem. N and M are the lengths of the two arrays respectively, and each of them is not empty and can be reach a length of 10 to the power 5th. In other words, we should avoid purely solving this problem by brute force. So the last two basically is about the ranges of elements and the success variable. So with that said, we're going to look at one example. So as we said, so here we are going to use binary search. And basically we want to find a proper insertion point, which will be clear later. So let's first look at the problem, the example. So let's look at this example, example 1. So here the spells is 5, 1, 3, and the portions is 1, 2, 3, 4, 5. So here in this problem, the portions itself is sorted. So in general, this is not necessarily sorted a priori. So the success is 7. So let's see, we have 3 spells. For spell I equals 0, so we have its strength is 5. And in order to achieve success state with the current given requirement, we need the portions has a strength at least 7 over 5. That is 1.4, right? 1.4. So then actually we notice that so in this portions, after the first element, all of them has a valid strength. So this contributes to 4. In other words, we have 4 successful matches for spells at index 0. So when I equals 1, so we have 1. So in order to have a successful match, so we need at least such a strength, that is 7 over 1, that is 7. But in this portions, there's no element that is greater than 7, so we get 0 matches. So when I equals 2, so the strength of the spell is 3, and the needed strength in portion is at least 7 over 3. that is roughly 2.333. So there are three portions, that is 3, 4, 5, satisfies the condition that we have 3. So the return will be 403. That's the result. So basically, if we look at the insertion point using a binary search, so basically for this one, the insertion point of 1.4 is here. So the index is 1, and the numbers in the right of this index is actually the number of successful matches. That is the length of the portions minus this idx, right? That is 5 minus 1. So for the second one, actually, the insertion index, if we do binary search, will be 0, 1, 2, 3, 4. That will be 5. So then the contribution will be idx. Length minus idx is 5 minus 5 is 0. So similarly for this one, the insertion point index for 2.3 is this one. It's going to be 2, right? So then this contribution will be 5 minus 2 equals 3. Therefore, we have 403. So that's basically the walkthrough of example 1. So now let's look at the solution. So the solution actually is sort of routine. We are going to use a bisect module directly, though we can write the binary search function ourselves. So from bisect, import bisect, so left in this case. So now let's first make some preparations. So let's first sort the portions. So this portions sort. So this sorts portions in place. Then I'll introduce the n and m is the length of spells and the length of portions respectively. Now we just need to do a simple for loop for I and spell in enumerate spells. Okay, it's maybe good. Let's first do something like this at the very beginning. This always maybe and here. So we specify the return. So the return is a result which we initialize as zeros at each position. So it's n, right? So in each in this for loop, so we for the current spell, say s, in order to have a success, so we need a lower bound. The lower bound is success over s. By the requirement, by the constraint, the spells has a range that is positive, so the division is always good. In other words, there's no division by 0 problem. So we get this one. Now we want to find the insertion point. So the insertion point, insertion idx. So here we are using bisect left. So that is the target. The search is basically in portions, and we search the insertion index for this lower bound. So due to the definition of bisect left, so which means that all the elements left to this insertion index is strictly less than the lower bound, and to the right is greater or equal, right? Then the contribution in this index will be the length of the spells, that is m, minus insertion index. So then with that done, we are ready to return the result. So let's check some special case. So insertion index, let me insertion index. So let's run this again. So or here. So let's try I. So yeah, this passes the first example. Now let's try the second example. So this is spell and portion and success. So let's try this. Yeah, it passes the special cases. Now let's look at the generic case. It passes the generic case. Yeah, actually, if we want to know some finer details, actually we can print out the insertion index at index I. So the insertion index is basically insertion IDX. So you see, for example, for this one, let's check that. So you see, yeah, this is 1. So the contribution will be 3 minus 1, that is 2. For this one is 3, that would be 3 minus 3 is 0. For this third one, the contribution will be the index will be 1, and the contribution will be 3 minus 1, that is 2. So yeah, up to now, I guess that's it. Thank you very much.